Hello and welcome back. We're going to pick up on one of the issues I've been talking about with memory fragmentation within Python. What we are looking at on the screen is a simulation of just that, where each of these boxes represents what Python calls an arena, or 256 kilobytes of memory. An arena is what Python allocates as a chunk for every time it needs to go out and get memory from the operating system. One of the issues with this, particularly with dictionaries, lists, or sets, is that if you use these over time and they begin to grow and shrink dynamically, like the program I have in the article below that actually demonstrates just how this happens, memory becomes fragmented. And that's what this actually represents when you look at the differences between each of the boxes. The green items are the most active, the orange items have already aged, and the red items have been deallocated, sitting in memory waiting to be taken back by the allocator. Now first, let me state that this entire discussion is very oversimplified for the point of context. Memory management is a philosophy all of its own within computer science. So the entire discussion here is kept to the most basic contexts because it can get very heavy. It can become obscenely technical, more so than I want to get into for conveying the problem that I'm actually trying and did finally manage to solve. So let's start with the basics of a dictionary, an empty set. That empty set sits someplace in memory, but as we work with the dictionary and we begin adding keys and values, those keys get allocated in different places, depending upon what is available in memory to fit a given size. And then when you begin to add more and more, they begin to fill up in memory in different places. Over time, this causes pockets of memory to be empty. Now, Python gives memory back to your operating system, but the rules of that are it can only give back one arena, meaning the entire block has to be unused. That is a problem for large dictionaries because large dictionaries can be scattered all over the place, and there needs to be a way to actually consolidate that dictionary. Well, there's two ways of going about it. The first way is the easiest. Your dictionary equals, and this does work for the dictionary hash table. That's your keys. Now the hash table is, think of it like an index. It points to the actual memory location your key might be at. But when you actually remove that key, that location goes back to the operating system to be reused. But the dictionary index, the part of the dictionary that grew to handle that new key, doesn't shrink. So if you have 10,000 keys and you delete 2,000 keys, you still have the space in the dictionary hash table for the full 10,000 keys. The hash table doesn't actually shrink unless you run the dictionary command I just displayed. Then your hash table is completely rebuilt. But that's the first problem. The second problem is actually much more complicated because that's the value part of the key. And the value part can be allocated anywhere as well. So if you've got a value that is, say, 400 characters, and then another value that's 800 characters, if you reassigned the 800 character value to say something that's 100 characters, you now have a dead zone at 700 characters still associated with that slot. Fragmentation. This is where the problem of the D equals dict D does not solve. This fixes the hash table only, consolidates the hash table, empties out the unlisted registry. But if you have values scattered everywhere across memory, you still can't return memory back to the operating system because it's still in use. The entire arena must be unused. If so much as even 1 byte sits in that arena, Python can't release it. So the only way to do this is with a technique called JSON washing. JSON washing uses the JSON package to rebuild a dictionary, both key and value, in a way that forces it to completely use new memory, or to completely move it out of the old memory. It's basically the approach of defragmenting that is used on your disk. You make a complete copy of everything in a new block of memory, and then you give back to the operating system everything in the old block of memory. You've defragmented your dictionary, and that looks something like this. D equals JSON loads, JSON dumps of D. This looks convoluted, and it looks like it actually does nothing, but it actually does quite a bit. And that is the biggest part of what this whole thing is. See, this is written entirely in C, meaning the JSON package. So it works very fast within Python. It's not like Python interrupting the process like it would be if you actually wrote this out in a complete new framework. Meaning if you actually went through your dictionary line by line, copying key and value. This does it completely different because you're converting it to a string. That string is one new large allocation. That's the secret. Because you're collecting that string as an allocation, you've collected all of the scattered fragments throughout your memory and put them together into one pot. The JSON loads then converts that single pot back into a working dictionary. So it effectively moves all of the fragmented pieces of your dictionary into a one linear piece of RAM. Now it can cost you 3 times the size of the original dictionary, which is fine. In fact, if you're used to just regularly fragmenting your disk, you already know that you can't defragment a full disk. You have to have space on that disk in order to defragment. This is the same principle. It works great, but it has a price. That one being 3x the memory, and second, it takes some time. Now for the context of Jackrabbit DLM, where this is actually used, because it's a server and the locker list grows enormous. Once an hour, or once under certain conditions of extreme memory freeing, I run this kind of a command. This is how I'm able to keep the locker online using plain Python or vanilla Python. No fancy memory tricks. It's because this does everything for me in standard Python. But that really is the contextualization of memory of a long-standing program. And I say long-standing because this applies to servers. It applies to programs that do any kind of deep analysis where a lot of data is moving. Normal data analysis causes large-scale fragmentation by default. You can't test, rate, and analyze several gigabytes of data without having that problem. Now, normally the Python allocation system works fine, but servers or large data loads do have special considerations. And you can force collect with the garbage collector in Python, and that works if you've got your memory in a contiguous block where you've emptied out one of your arenas already. The garbage collector will give empty arenas back to the operating system, and you can actually see that in applications like HTOP or just top, where you see your RSS drop. But under normal Python usage, that doesn't actually take this problem into consideration. Your memory will never go back. It will just climb and climb and climb until finally the operating system kills the program. So once in a while, if you have any kind of large data analysis, you need to consolidate that data into a solid chunk so you can give back to the operating system and keep your program running. Nothing is more infuriating than doing a data analysis and having the operating system say, your program got too greedy, so I killed it. So when you look at this kind of a framework, at this kind of a situation, understanding how important maintaining that is critical. This is an advanced theory, an advanced problem. But from the standpoint of Python, it's not talked about enough. Most people will just tell you you're using the wrong language, or you should use a different language that's better suited for your task. And that's actually not correct. Every single programming language has to deal with memory fragmentation in some way. Now, there are different languages that actually have different ways of doing it, including measuring that fragmentation and forcefully reconsolidating on their own. But that costs time. That slows the program down. So there's always those trade-offs. You could either do it yourself with C, assembly, machine language, or some other unforgiving approach, or you can use a high-level language like Java, Python, or so forth, and let the machine worry about it, but then you give up control of being able to decide when that goes back to the operating system. Or the third way, which is what I'm demonstrating here, you can help the operating system make decisions by forcefully consolidating certain things in a new block of memory. It's not a perfect solution or situation, but it keeps Python functional for a long-range server or deep data analysis, because you've been able to actually deal with a real-world problem, making sure your program doesn't get too greedy and take too much memory, by making sure that over a course of time you can actually shrink your memory. Now, the program that is in the link below, or in the message below, depending upon which way this goes, whether it's on Patreon or YouTube, that program demonstrates this entire process, where I actually ended up running it, and I show exactly what happens, the entire process, how the hash table gets fragmented, and how the key value part gets scattered throughout memory. For my system, I did a test of 500,000 keys. Those keys by the time I got done running my test, caused me to use 53% of my memory. By using just this technique, I was able to reclaim 851 megabytes of RAM directly, going back to the operating system. So one line of code gave that much back to the operating system by cleaning up what I was doing. So this type of technique doesn't take a lot. It doesn't require a lot. But if you don't know what's happening, if you don't realize that your memory is becoming fragmented, it will crash your computer. And that's exactly what happened to me. When I was working on the DLM, I had just done a large test to really pressure test it, and it wasn't giving the memory back. I had ended up using 15% of my RAM in that test. I figured it would give itself back over time, but it didn't. Hour after hour, it just kept growing. The fragmentation just kept getting worse, until finally it took down my server. My server ran out of memory because the program got greedy and it didn't clean up after itself. Adding this line fixed that problem. Figuring out how often to run it because of the cost is a different story. And that's something that only you can do through trial and error and actually watching the program. But that is the whole point. This problem is very fixable once you understand it. So let me know what you think. Share your thoughts, leave a comment, ask questions. Python is still a wonderful language, but understanding it can sometimes be a little strange, especially when you're just beginning and you run into this kind of a problem where you don't know that your memory is actually being fragmented. Read the article below, leave a comment, download the test programs, try them yourself, look at the code, and see exactly this process on your own machine. Thank you for watching.